Students, now let's continue. We are going to see how a matrix can be constructed from a given condition. So you are given a matrix A having entries Aij with size 2 by 3, satisfying this condition. So every element here Aij is going to satisfy the upper condition if I is less than j, and the lower condition if I is greater than or equal to j. So we are expected now to construct a 2 by 3 matrix right here. So let me show you how this can be done. So as you see, the solution goes like this. Now your matrix is a matrix of size 2 by 3. So you just label every element here in this matrix with size 2 by 3, saying A11, A12, A13, A21, A22, A23. You just do this because the size of the matrix is already determined, so you have to adjust in such a way. Okay, if you observe now the size of this matrix, it is having 2 rows and 3 columns, so we are right. So what I need to do next is look at the subscripts here. The first one is A11. As you see, A11 has I1 and j value 1, so I is now equivalent to j. So in the case where I is equivalent to j, you need to use a lower expression, 3i minus j. So you need to put 1 here in I and minus the j is again 1, so 3 times 1 minus 1, which actually is 2. And if you see the right one, it says A21. So in the case of A21, the I part is 2 and the j part is 1. So clearly I is greater than j, so you need to use the lower part, which is 3i minus j. So 3 times 2 minus 1 is going to be used. So in place of I have 2, and in place of j take 1, and this is going to be 5. Similarly, you can list the others as you see. A12, here in the case of A12, I is less than j because I is supposed to be 1 and j is supposed to be 2. So in case I is less than j, you have to use the upper expression, which actually is I plus 2j, so 1 plus 2 times 2 is going to be used, which actually is 5. For A22, the case where I is equal to j, we are having now the lower expression, 3 times 2 minus 2, which basically is 4. So what's left now, A13 and A23. So A13 is, you see, the case where I is less than j, so this is, you see, the upper case, so 1 plus 2 times 3, which actually is 7. And the last one is A23, which basically is the case where I is less than j because 2 is less than 3, so in place of I take 2 and in place of j take 3 for the upper expression, because the upper expression is used for the case where I is less than j, so directly use 2 plus 2 times 3 because j is 3, and you get 8. So every entry is now obtained for this matrix A. So your matrix A is going to have these entries. So when you read this in rows 2, 5, 7, 5, 4, 8, this is how the given matrix is constructed. And when you go to the second one, given a matrix A of size 2 by 2, as you see, you are asked to find A the power of n of this matrix. So how can you find that? Your A square is 1 to 0, 1, 1 to 0, 1, so you need to multiply A twice. So as you are multiplying this twice, you are going to have, as you see, this expression. But remember how you can carry out the product of two matrices. I hope you recall that. So in the case of this, you multiple, you see the first row, the entries in the first row with entries in the first column. So 1 times 1 plus 2 times 0, as it has been stated here. And when you come to this, this basically is an entry obtained at the intersection of first row and second column. So you need to take the first row entries of the first matrix with the second columns of the second matrix. So 1 times 1 plus 2 times 1 is going to be taken. You do the same for this one. This basically is an element obtained at the intersection of second row and first column. So you have to consider the entries of the second row and the entries of the the entries of the first column in the second matrix. So as you are doing that, 0 times 1 plus 1 times 0 is going to come. Do the same for the other entry. So finally you will obtain this one. I intentionally wrote here 2 times 2. Actually it was 4, but I intentionally wrote this one in terms of this because you will see a certain pattern, and from that pattern you are going to deduce what is a power of n is going to be. Okay, so now a cube is going to come. A cube basically is, this is the one you calculated here. A square is going to come here. A square times a, so a square is already calculated, so a square times a is a cube. So what I need to do is you do the same thing as you did above. The product rule shall be done. So when you carry out that again by the same procedure, you will encounter this expression eventually. Look, I wrote again here 2 times 3 intentionally because I do have something to talk about, the exponent appearing here and the multiplier of 2 in the given matrix. So proceeding this way, what comes next is a power of 4. So clearly a the power of 4 is a cube times a. So a cube is already done. It is 1061, so it's written here, and a is here. So try to multiply that again. So as you are multiplying this by using product rule as we did above, you will encounter this kind of expression. So 2 times 4, 0, 1. Do the same for a the power of 5. Actually we are able to determine by considering the first 3 outputs, but let's assure by doing a the power of 5. So students, again, a the power of 5 is nothing but it is a the power of 4 times a. So here a the power of 4 times a is going to be used, and as usually the final output is going to be 2 times 5, 0, 1. Basically you need to use the product rule whenever you multiple. You see these matrices, according to this product property, you have to have such output. Now guys, from this pattern, what do you understand? I want to tell you about that. Look, here you're having 2. What's happening here is, you see, 2 times 2. Here you are having the exponent 3. Here again 3 comes. Here you are having 4. The same comes, 4 is going to come. What about the rest? The rest are as they are. Look, throughout all this you're having 1 2 0 1 1 2 0 1 1 2 0 1. What's happening here is 2 3 4 are written, but these 2 3 4 are directly taken from the exponents here. Okay, so if you come to the last one, it says a the power of 5. So as you see, 2 1 2 0 1 are written as we were having before. So 5 is directly coming here. For instance, had you been asked to find a the power of 6, what can you say? Had you been asked to find a the power of 6, this would have been what, students? You see, a matrix with entries. Let me just read in raw form. 1, 2 times 6, 0, and 1 can come. So from this pattern, one can easily conclude that, a the power of n will have, okay, this kind of form. You see guys, 1 square 0. Look, in the case of 5 you took 8 because 2 times 5 minus 2 is 8. In the case of 4 you took 2 times 4 minus 2, 6. The same is going to come in the case of power of n. 2 times n minus 2, which actually is 2 into n minus 1, can come. And here it is, you see, a, which actually is basically a the power of n minus 1 times a is going to come. And as you calculate this, the final output is going to be like this. So whatever n value you may use, you see the output is going to be 1 to n 0 1 matrix. So for example, had you been asked to find a the power of 100, what can you say about the final output then? Simple. It's a matter of putting 100 here in place of n, and it will be 1 200 0 1. So a matrix with entries 1 200 0 1 can come. So for every power of n, now we can express the equivalent output of the matrix in such a way. I hope you have understood.